Hello and welcome. This is an introduction to the data and error analysis. Ordinarily, we would collect this, um, after the first or second lab meeting. We're going to collect this semester at the start of the third lab period. So you'll have the first week of the semester to work on this activity. We'll try to do a lecture on data and error analysis in person. I'll get the slides and the recording of that lecture posted for anybody who can't make the lecture. So hopefully you've already seen that lecture before tackling this activity. The purpose of this video here is for us to be able to interact together, but without necessarily interacting so closely together. So this might be an easy way for you to be able to accomplish your work is through watching videos throughout the semester. Um, what I would recommend is as you do this activity, just hit pause, maybe have your phone or an iPad playing the video and your worksheet where you're doing your work separately. So the first example here is we're doing and using the error propagation equation as discussed in the lecture notes. So we're going to evaluate the expressions for f and delta f. And we're given that x is equal to 75.0 plus or minus 0.5 meters and y is 25.0 plus or minus 0.5 meters. And we're going to do two examples in this page here. F is x plus y and f is x times y. So obviously you just take the two x and y values, add them together. Obviously they come out to 100, nothing too tricky there. The issue is the delta y, or the delta f, excuse me, the uncertainty in f is not simply obtained by taking the error in x and adding the error in y. It'd be nice if it worked out so simply, but it doesn't work out so simply. What we need to do is take the partial derivative of f with respect to x and then multiply that by delta x. We're squaring both of those terms. So take the partial derivative with respect to x, square that, multiply by the uncertainty in x, square that term. And then take the uncertainty, for the uncertainty in the y chunk, what you do is take the partial derivative with respect to y, and then square that, and then multiply by delta y. Now df dx, so think, what's the partial derivative of f with respect to x? Well, it's just 1. It'd be 1 plus 0. So in the case of taking the partial derivative with respect to x, y is just simply a constant. So that's why the df dx is just equal to 1. And df dy is also equal to 1. So we're going to have the result be 1 squared plus delta x squared plus 1 squared times delta y squared is hopefully what you simplify that down to. And that's the uncertainty in f squared. So at the end, you got to take the square root of that analysis. And then when we do x times y, the only thing that changes is df dx is now y, and df dy is now x. You can use Wolfram Alpha or other differentiations solvers throughout the course. This isn't a calculus course. So if you need some help doing, maybe not with this equation, but more complicated equations throughout the course, be sure to use technology to your advantage. Now, what you can work out here is x times y is now 75.0 times 25.0. And then you can work that out and then work out your plus minus. A couple things are your f plus or minus delta f should match in decimal place. So let's say you work it out to be 100.0. I can't remember what the actual answer is. Let's say you work out the delta y to be 0.34. You'd want to round your uncertainty in f to one placeholder. So in that case, if it's 0.34, that'd be to 0.3. And then you'd want to match the 100 to the same decimal place, so 100.0 plus or minus 0.3. Okay. So then the other issue is, well, what if we just followed sig fig rules? If we just, sig fig rules would be 75.0 plus 25.0, we would end in the decimal place of the tens place because, you would round to the placeholder that's greater in quantity, and they're both to the tens place, so the result should be good to the tens place. I think that's what you're going to find from your analysis with the error propagation equation is that it also was reported to the same placeholder. The same thing about x times y. It should be 3 sig figs. 3 sig figs times 3 sig figs. The result should have been rounded to 3 sig figs. You can then look at your result and see if it was rounded to have a total of 3 significant figures. So think about that. So the issue here with sig figs is that significant figure rules are really just a generalization of doing this more formal analysis. It's sort of generalizing the rules so you don't have to do this analysis. So you know where to round your results from generalization. But of course, you could also attach some specific uncertainties, work out the precise values, and then see that you generally find that the results are, as precise as they were with the sig fig rules. Just now you have a better characterization of what the specific uncertainty is in your final result. Then we do an example with a more complex equation. Here we get x times y cubed divided by z squared, and we have our values here. And so you can determine f and delta f. So you're taking, df dx, df dy, df dz, slightly more complicated, but not too complicated in terms of their derivatives. Remember, take the partial derivatives with respect to each variable, square it, and then multiply by the uncertainty in that variable squared. Add all those up, and then ultimately take the square root. If an interesting question would be the limiting source of error would be the term that's biggest. If you take the df dx, square it, times delta x, square that, versus df dy, square that, times delta y squared, and the same thing with z. Which of those terms is biggest? If you imagine having the uncertainty with respect to x, and then y and z is like three chunks. You have like the a plus b plus c, where a is just your df dx squared, delta x squared, b is your df dy squared, delta y squared, and c is df dz times delta z squared. Which of those chunks is biggest? Whichever one is larger is the limiting source of error. It's the one that you'd want to reduce. It's the error source you'd want to reduce the error in to have the greatest impact on reducing the magnitude of error in f. So determine f, delta f, report them with proper sig figs, and then you can go to Excel to reduce each variable by a factor of 2, like one at a time. So you want to kind of come up here and say, okay, cut this by a factor of 2, cut it in half, cut this in half for y, or cut the z term in half. But when you cut the x term in half, use y as plus or minus 5 and z as plus or minus 0.04. Okay. And then all else is the same. So you can report your delta f from part A, and then change x to 10. Everything else is the same. Change y to 2.5. Everything else is the same. Change z to 0.02. Everything else is the same. What you're really testing out is your hypothesis, your result up here of the limiting source of error. Does cutting the limiting source of error in half lead to the greatest reduction in the uncertainty in f? If it doesn't, we probably misidentified that limiting source of error. We can go back and take a second look. Now moving ahead, we have a linear regression. Sometimes we have to do these in the class. I'm going to put up a second video specifically geared towards using the Linus function. You could also find general videos as well on the internet. But I'll put up a specific video on how we can use the Linus function to give us the slope and the intercept here and their uncertainty values. And then finally, the last thing is just going through some arithmetic of calculating a mean, standard deviation. So standard deviation is just the deviation of each point squared divided by the number of data points minus 1, taking the square root. Standard deviation of the mean takes the standard deviation from above and just divides it by the square root of the number of trials. And the 95% confidence limit, I think we discussed this, or we should have discussed this in the notes preceding into this activity, but you have to look up a t-value from a chart. So you look that t-value up, and then you multiply it by the standard deviation of the mean. So what this is doing, the standard deviation of the mean would be what's the 68% confidence limit of the mean value of where it lies in the distribution. So if you collected all these data points here, your differences are the standard deviation of the distribution tells you 68% of the measurements fell within the plus or minus s. The standard deviation of the mean tells you how confident you are of where the mean value lies. So it gives you the 68% confidence of what the actual mean value of the distribution is. So it's a little bit of a difference in terms of what the distribution mean, or what the distribution looks like in terms of its width versus your confidence in the mean. So two slightly different standard deviations and how they what they mean. And then you have the confidence limit. You can say, well, if I want to be 95% confident in establishing the mean value of the distribution, then we need to expand the uncertainty to be a larger value. So you look up the t-value for the 95% confidence limit in a chart, multiply that by the S sub m. It makes the value bigger, it makes the plus minus bigger. so that you can then have a greater confidence that the mean value lies within the plus minus values. I essentially, I think, just answered what part E is, but part E is just going through what all these different things mean. And then finally, a Q test is the a test that you can use to see if you can reject a data point. What you'd want to do is try to find the data point that's the furthest away from the other values. I think there's one that really stands out, that 3.2. Here looks to be quite far away from the others, so you can try to establish taking the gap versus the range, and then look up in a chart for at least 90% confidence to be able to reject a data point. But again, this should have been discussed in the slides coming into the activity, so hopefully you have some idea of what a Q-test is from those slides. Okay, so that's a quick introduction to this activity. Um, you know, probably some of you guys will be working this at home. You can email questions if you have them. Same thing throughout the course, or if you're in person, feel free to ask us. We're happy to help. We just hope the video helps, these videos throughout the semester help reduce some of the interactions we might have due to our current situation. All right, thanks for the attention.